And it came off as like, that's how I feel. And it's, so basically said no, you're free.
Yeah, you can buy them in fees. It's only they're really fees.
They were told never mind your people.
You don't have to, well, I mean, it's good if you buy like a plastic in there. You can buy like a little plastic.
There's a lot of work. Like, I can get them on virtually.
Go on Amazon and find a used. What?
My Yuki came off.
And it said that we had to buy a couple of keyboard, but my sister has bought like a little piece. Okay, I see why they know. So that it can like my sister's has this little piece on the side that can
All right, is everyone ready? Ready you're going to get? All right. On our reminders, announcements, the 2 homeworks that are due this week, one is tonight, one is Wednesday, no homework Friday. And then you'll have 1 homework next week. The exam is next Wednesday. Yay. And then we'll start talking about some stuff that you guys are more familiar with, like gas loss and thermodynamics and things like that. So we'll venture back into some familiar territory. All right, so Friday, we finished up talking about how you have different levels, different sublevels, different orbitals, how you put the electrons in. So now we're ready to take that information about electrons and apply it to what we know about the periodic table and how periodic properties are based on electrons. Question first. 8. Which will be the last chapter on the exam. So the exam will be 1, 2, 7, 8. All right, so the periodic table. The credit goes to Dmitry Mendeleev for developing what we call the modern periodic table. The table is based on the periodic law, which we mentioned a few lectures ago, but the periodic law states when elements are arranged with increasing mass, properties occur periodically. All right. Which is fine, that's correct, right? We had, I think on your homework, maybe 2 homeworks ago, it talked about things in the same column having similar properties, and they said if you're in this column, what's another element that's similar to it? Is our current periodic table based on mass? No, what's it based on? Atomic number. Atomic number tells you number of protons. So our current periodic table uses increasing atomic number rather than mass. That's because there's some swirly masses in there that don't line up correctly. Like cobalt and nickel, technically cobalt is heavier than nickel, but cobalt's 27 and nickel's 28. So it works out better if we use atomic mass. You get a better lineup of properties. So if the periodic table is based on atomic number, which is the number of protons, and we have neutral atoms, protons and electrons will be equal in number, which means truly the periodic table is based on increasing number of electrons. So if the atomic number is increasing, really it's the same thing as saying It's based on increasing number of electrons.
What is based on increasing the positive? Which means also?
Oh, which means also? Which means also, yeah. So if it's based on the fact that the number of electrons are increasing as we go left to right, top to bottom across the periodic table, there must be some organized method by which we put electrons into an order. Good thing you already learned that. That's the quantum mechanical model. So, the quantum mechanical theory describes the behavior of electrons and atoms, which was chapter 7. All right, that's what we did in all of chapter 7, describe the quantum mechanical theory. So there's a few different ways we can describe how the electrons are found in an atom. And one way to do that is called electron configuration. So an electron configuration for an atom shows which electrons are in which specific orbital. Now, can we know exactly where they are? No, we don't know exactly, but we can make a best guess as to their 4 quantum numbers. We can make a pretty, based on probability, a pretty good guess of where they're going to be. So, let's start with hydrogen. I think we're ready for hydrogen. Hydrogen has an atomic number of 1, so how many electrons does it have? 1. We are ready for that. All right, so let's use this. That's my example. Right? Hydrogen has 1 electron. So, thinking through, if it has 1 electron, we always have to start in the lowest energy level. So, what value of N has the lowest energy? 1. All right, so if N equals 1, what does L have to equal? Okay, what about M sub L? 0. Okay, that's the lowest energy configuration you can have for an electron, right? Lowest energy, there's only one option for L and M sub L. What if I wanted to know M sub S? What would it most likely be? Positive. We usually do positive first. So usually plus 1/2. That's an S, not a G, though. It's kind of crazy. Yeah?
In what cases would it be a negative?
You're not ready for that.
Oh.
Yeah. When we talk about, yeah, some other case, we'll see an occasional case where it's negative, rare. You know, just go ahead and say it's always going to be plus first. We'll just make that the rule for this class. Always going to be plus first. All right, so this is handy, right? This is all the 4 quantum numbers for that 1 electron. Man, it'd be nice if there's a shorthand way of writing that so I don't have to write it all out every single time. Good thing there is. So, I want to write in shorthand. So I need to tell the reader what energy level it's in. So what value do I give the energy level? 1. All right, I want to tell the reader what sublevel it's in. So what letter do I need to tell them? S. I now need to tell the reader how many electrons are in that 1s. So how many electrons do I have? So you give it a superscript. So that tells the reader N equals 1, L equals 0, and there's only 1 electron in it.
Can you do that one more time?
Sure. So 1 comes from N, these two. Then S comes from L. And that 1 just tells me 1 electron.
And that comes from the actual number
Yep.
right there?
Yep. So that tells the reader most of the information. Does it tell the reader all 4 quantum numbers? No, it just gives them kind of, you definitely know the energy level, you definitely know the L, And you know there's only one electron, so it doesn't tell you everything. It tells you most of the information. If we wanted to tell the reader more information about the electron, we would use an orbital diagram. So an orbital diagram is a graphical representation of the electron configuration. So an electron configuration is using really words. A graphical representation is going to be the orbital diagram. So let's use our same example of hydrogen, where it says 1s1, which is the electron configuration. If I wanted to do this as a graphical representation, you draw one platform or one box for every possible m sub L. So this is my 1s platform. How many m sub L's are possible in 1s? Just one, right? There's only one possible m sub L for 1s. Can only be 0. There's only one possible platform, right? Only one orientation. How many electrons live in that orbital? 2 possible, 1 currently. So I draw a half arrow facing up. So in this picture, I have now told you all 4 quantum numbers. I told you that n equals 1. I told you L equals 0. I told you that m sub L equals 0. And it's plus 1/2. So if I use the graphical representation, you get all 4 quantum numbers. Or if you use the electron configuration, you really get 2. Maybe you can extrapolate the third, but for sure 2. Right, and the direction of the arrow shows the electron spin, so I'm showing it. It's your option. Some textbooks use a half arrow, some textbooks use a full arrow. I find a half arrow faster to write. Both are correct. All right, so what if I had 2 electrons? You guys ready for that? 2 electrons? Okay. What element would have 2 electrons in its natural state? Okay, helium. Okay, let's write out the electron configuration first. So doing it in shorthand. It has 2 electrons. What energy level are they both in? They're in the n equals 1. Sorry, I said I'd do this one first. 1. If they're both in n equal 1, what L should they have? S, right? 0, S. How many electrons are in my 1s? 2. So that'd be the electron configuration for it. If I wanted to do the orbital diagram, you would get the same platform that hydrogen has. But how do I show that they have opposite spins? Yeah, 1 up, 1 down. So now if I wanted to, I could pull out all 4 quantum numbers for both those electrons. So far, so good? Okay. It is the same thing. I just thought I'd write it out in case you were confused, right? N goes to the number, L tells me the letter, number of electrons. This is the electron configuration. This is the orbital diagram. I prefer platforms because I'm better at drawing a straight line than I am a box. But if you feel strongly, feel free to write boxes and fill in the boxes. Both are fine. So the orbital diagram tells me the same information, just graphically. All right, you ready for electrons with more than two electrons? You guys ready for this? Okay. Because actually, most of the periodic table has way more than 2 electrons. So, all right, in both hydrogen and helium, the energy of the orbital just depended on the principal quantum number. Which letter is the principal quantum number? N. If you have atoms with greater than 2 electrons, which I think is like 99% of the periodic table, the energy depends on L and N. So, thinking about this, right, we draw our little, this is energy. Right, you have that energy level diagram. If I have an N equal to 1, right, we already said we can only have one value of L. All right, you only have one option. If N equals 1, then L is 0, and M sub L is 0, right? What if I have N equals 2? What are my options for L? So then if I do M sub L, I have to actually do 2 sets of M sub L. So how many orbitals are possible if N equals 2? 4, right? 4 different possible orbitals. If L equals 0, then it's 0. If L equals 1, then it's these 3. But altogether I have 4 different options. The catch is if I have an energy level of 2 in my atom, it means I must also have an energy level of 1. They both exist. So if I have energy level 2, it really means I have N equal 2 and N equal 1 in my atom. They're both happening. So if I have N equals 2, it has 4 orbitals. N equals 1 has its 1 orbital. So whatever that atom is, has 5 orbitals altogether possible available to it. So when we think about where to put the electrons, we're going to go low energy first, then to higher energy, then to higher and higher energies. So these are slightly out of order. I'm going to do lithium, then I'm going to go forward, then I'll come back to my example. I changed my mind this morning about what I actually want to do. I think it worked out better this way. So let's work through what lithium is, then we'll talk about this, then we'll come back. All right, lithium, how many electrons does lithium have? 3, right? 3 electrons. So, since I'm more of a graphical person, I like to draw the picture rather than the words, but both are fine. So this is my 1s platform that we've had before. How many electrons can live in 1s? 2. Is that lithium? No, right? Because that's helium. It only has 2 electrons. But I got this 3rd electron out there. So what energy level must it be in? Okay, if it's in 2, jumped ahead of me, yeah. So if it's energy level 2, what's the lowest energy sublevel in 2? S. So then how many electrons do I put on that platform? Just 1. That makes sense? So far so good? N equals 1, L equals 0. Each have 2 electrons. Then N equals 2, L equals 0. With 1 electron, we work our way from the top.
Okay, so as far as like form one, I from the bottom because n equals 1, so your L would be 0, so L would be S.
Yep.
And then 2, n equals 2. So could
Yep.
it possibly be P instead of S, or would it be always
L being 0 is of lower energy than P being 1.
even though n equals 2, but can L also be 1 or 0?
It can be, but 0 is less energy than 1.
Okay, so you want it on
So
the
you do
left
0
hand.
first.
Okay.
Yep.
Okay, that's what I was thinking.
That's a good question, though. So 0 always wins. All right, I'll come back to this slide. Okay. Turn too many pages. All right, so the energy of orbitals goes low energy to high energy. All right, so energy of orbitals goes low energy up to high energy. We can now start talking about how to build up electrons in orbitals, low energy to high energy. We're going to use two rules to help us figure out what order to put the electrons in. I'll come to that one in a second. The first one's called the Aufbau principle, which states what we just said. Fill in electrons lowest energy to highest energy. So you're going to fill it up all the n equals 1s. Then if n equals 2, S is less energy than P. I can even draw a little picture down. Hold on, let's see if I can figure out how to draw this picture. It only has one option. Something like that. It's not 100% right, but that's the idea. So the lowest energy, n equals 1 and L equals 0. Then when you jump up a level to n equals 2, 0 is going to fill before 1. Then going up to the next one, 3, 0 will fill before 3, 1 will fill before 3, 2. So the bigger the L, the more the energy, so we have to go, you always put them down here and then we go up that way. Okay, good. All right. So we just did lithium. Let's do a challenging element like nitrogen with 7 electrons. Okay. All right, we got 7 electrons. So what's my first platform called? 1s. And how many electrons can I put in 1s? 2. 2 lives on every platform. There we go. All right, I got 5 electrons left. What is my next platform called? 2s. And that can hold 2 electrons. Now we're up to 2p. How many orbitals are in 2p? 3, right? There's 3 possible options of m sub L. I'm going to tell you, the reader, that there are 3 possible orientations by putting out 3 platforms. Right, because the platform tells me the m sub L. In this case, there's only one m sub L. In this case, there's only one m sub L. In this case, 2p could have m sub L of -1, 0, +1. So you're telling the reader, there's 3 options. We're going to fill them up lowest to highest. So which of those numbers, based on your knowledge of the number line, is the smallest? -1, 0, or +1? You guys are all so smart. All right, so far I have 4. So I'm going to put 1 electron in -1. Where do I put the next one? I'm going to put it over here in 0, and we'll use Hund's rule here in a second. 3. So Hund's rule tells me an electron would prefer to be on its own platform rather than share. I mean, I think everyone would, in general, would prefer to be on your own space rather than share space. So Hund's rule says that we fill degenerate orbitals by filling them singly with upspin first. So degenerate means all of the same energy. So these 2p orbitals are all degenerate. They're all equal to each other. They all have the exact same energy. So that being the case, we're going to put one electron on each platform, and we always put them spin up first. Okay, we're ready to go back and try magnesium. Challenging magnesium. All right, so we have magnesium. Magnesium has 12 electrons. So what is the first platform called for magnesium? Will always be 1s. And how many electrons can I put in 1s? 2. All right, I got 10 electrons to go. We're making progress. All right, what's my next platform called? 2s. And how many electrons does he get? 2. All right, what comes after 2s? 2p. And how many platforms? 3 platforms. So I'm going to fill them up first. 1, 2, 3, and then come back. 4, 5, 6. So now I have 10 electrons, right? I need to have 12 total. Can I do 2d? No, right? Not allowed. So what do I go next? 3s. How many electrons in my 3s? 2. You probably heard about this in high school, right? Like you probably could count across the periodic table. 1s1, 2s2, 2p6, 3p2. Now you know why. So that should be good. All right, I think you guys are ready for my challenge question. All right, so in order to answer this, we're first going to do the orbital diagram, figure out which electron's the quote-unquote last electron, and then write down its quantum numbers. All right, chlorine has 17 electrons. So how many more than magnesium does it have? Right, 5 more than this guy. So its electron configuration is going to be this plus 5 more. So we can go ahead and just skip right ahead and for sure do those ones. Okay, so I've used up 12. What comes after 3s? 3p, how many platforms? 3. 1, 2, 3. All right, so then we're going to fill it in, and I go up first. 12, 13, 14, 15, 16, 17. So that last one I'm going to circle. This is the last one I drew. I want to know what 4 quantum numbers does that electron have. So how do I figure out what the n is? Yep, so n is 3. How do I figure out what the L is? If it's p, what number is that? 1. Okay, M sub L. What is your good guess as to what the M sub L should be? I mean, probably 0 because it's in the middle, right? If we do -1, 0, 1, but I would accept all 3 because you're just making a good guess. If it's a facing down arrow, what should the value of m sub s be? Negative 1/2. So now we can go back and forth. We can use this information to draw an orbital diagram. We can use the orbital diagram to tell us about the quantum numbers of each one. Is the electron over here, can it have the same 4 quantum numbers? No. What, the way I've drawn it, what would be some differences in its quantum number? The m sub l will be different, and the m sub s would be different. What about the electron that's sitting right next to it? Right, it'd be a positive spin. So you can't have 2 electrons on the platform both going up, because they have the same 4 quantum numbers. So one definitely has to be up, one has to be down.
So on your test, would you give us the quantum numbers and ask us to draw in circle which
There's a
electron?
good chance I could do that. That's one of my favorite questions actually to ask. I try to keep it under 20. I try to only have, because after 20, it's a lot of, I'll show you some shorthand here in a minute of how you can get past 20.
So would you circle that arrow, or would we circle, would we choose which one?
You would probably choose which one is the outermost, or the last, based on knowing that you have to go lowest to highest, and go all up first, and then go down. So, yeah.
Why is it 0?
What was that?
Why is it 0?
Because I put it on the middle platform, and so typically we call m sub l minus 1, 0, plus 1. I mean, I would have accepted any 3 correct m sub l values, because you're making a good guess as to where it is. That's the least well-known part of that.
Is L an up arrow or a 1 up? This one pictures, right?
Which one?
The L on.
Oh, sorry, that's the number 1.
Okay.
That's the number 1, sorry. It does look like an up arrow. All right, we're now ready to try some trickier things. Oh, this is just a cheat sheet. Does anyone have their textbook, happen to have it on them? You don't have to, but if you did, can I borrow it real quick?
I have.
All right, I'm going to show you for your homework. Let me show you what you really need to have handy. So either have the e-book or the hardcover book. You're going to want to have this page. It's 298 in your textbook. It has all the electron configurations for every element already written out. 298. And so as you're doing the homework for tonight and for Wednesday night, this will be super handy, especially when you get into elements. I think there's a question about, like, one of these guys down here that has like 65 or 66 electrons. You're not going to want to write them all out. So this is how you can kind of skip to the end. Awesome. 298 in your textbook.
So how the test you do?
No. But as you're doing your homework, it's handy. I will have a question about 65 electrons. That's a lot of work. I try to keep it under 20. All right. So how do you know where you are in the periodic table with respect to the number of electrons? All right, so electron configuration, valence electrons, periodic table, how are they all related? All right, as we've seen in our last 2 or 3 examples, what do we have? We had hydrogen, right, with an N equal 1. Then we had lithium with an N equal to 2. Then we had magnesium with an N equal to 3. As you may notice on our periodic table, hydrogen is in row number 1, lithium is in row number 2, magnesium is in row number 3. So as you go down the periodic table, the N value increases by 1. And as you move across the row, left to right, the number of electrons increase by 1, which makes sense, right? Because it's based on number of protons. So if the protons are increasing by 1, electrons should be increasing by 1. as a caveat, n is constant as you're moving across. So if you're in row number 3, the highest n value will always be 3, but the electrons will increase by 1. All right, let's see here. All right, so electrons are critical in bonding and in chemical reactions. But only certain electrons in an atom are able to participate in bonding and chemical reactions. All right, so electrons are what you use if you're going to do bonding or you're going to do chemical reactions, but not all the electrons are available to participate. So as we look at, let's do, someone pick an element between 1 and 20. Who we haven't done? Silicon, 14, perfect. So let's look at silicon. 14 electrons. All right, doing what we've had before. I'm going to use electron configuration. You can certainly write an orbital diagram, but I'm going to do it this shorthand. 1s2, 2s2, 2p6, 3s2, 3p2. 10, 11, yeah. All right, so that's the electron configuration. Right, I could have written that as a one with the platforms. That'd be fine too. Which orbitals are in the highest energy level for this? Which ones are the highest energy orbitals? The 3s2 and 3p6, right? Those are the highest energy orbitals. The highest energy orbitals are called valence electrons. They have the highest energy because they both are at n equals 3. So those are called valence. And if you're not in the valence, then you're considered core electrons.
Core or
Core. Core, as in central. All right, so if you are a valence electrons, you are the ones that are available to do chemistry. You're farthest to the outside, you're the highest energy, you're the most reactive. Those are the ones that are going to be available to do work. Core electrons are not available to do chemistry, but why do you need them? You have to have the valence, and what would happen if I took out, how many is that, 10 electrons? It won't be neutral anymore, right? It would be supercharged. So we need the core electrons to stay neutral, and we have to have the core electrons so that these guys in the higher energy levels stay in the higher energy levels, right? Because if we took these away, these guys would be like, I don't want to be this energetic. I'm going to drop down to 1, because that's way easier. As most of us do think, I'd much rather be low energy, take a nap, than be doing all this work, out here, all this chemistry. So if we have core electrons and valence electrons, we can now talk about them doing chemistry. I'm going to show you one other shorthand before the end of class. So we'll start here on Wednesday, but let me show you some shorthand you'll need for the test. Homework. Test also, but definitely homework for tonight. All right, so, let's pick another element. Let's do sulfur. Great. All right, so sulfur. Let's write its electron configuration first. If it has 16 electrons. 16 electrons. So its electron configuration, let's see, 1s2, 2s2, 2p6. Now what? 3s, and how many in the s? 2, and then sulfur's 4 past that, so 3p4. Well, if I wanted to draw this as an orbital diagram, how many platforms would I draw for p? 3 platforms. 1 for 3s, 3 for 3p. Then you'd go and fill them in. Which one of those was the last electron to be placed? What platform is it on? The first, second, or third platform? Yes, that's the last one, right? So that's the last one you put in there. So if you're thinking, which one's the last? That was the last one you drew. All right, so we got electron configurations, we got orbital diagrams. A shorthand for this, so a shorthand electron configuration would say, all right, these guys are the core electrons, right? 1s2, 2s2, 2p6, those are all core. How many electrons are in the core total? 10. What element has 10 electrons? Neon. So you put a bracket, you say start with neon. Skip ahead in the periodic table, start with neon. And then what makes this element different is that it's neon plus that much. So mastering chemistry will accept either you writing out the entire electron configuration, or it will accept this shorthand. If you put bracket, element, now this one in the bracket must be a noble gas. Has to be an end cap, right? Because it doesn't make any sense if it's like start in the middle. So, but it's full. Yeah, it's a full complement of electrons. All right, we will stop there to give you enough time to do your quiz. You will need a calculator.